and welcome to the nature of molecules. So this is a brief review of what you had in chem class in high school. And the IntroBio book does have a chapter on it, but I don't want to spend a lot of time on chemistry. I'm trying to extract what we'll be working with and what I need you to know for this first semester. So very briefly, all matter is composed of elements. The main elements in the human body are hydrogen, oxygen, and carbon. And you'll learn more about that when you take Gen Chem here and Organic Chem here as well. So I'm not going to explain a whole lot of it, but just briefly brush over it. So each element is composed of atoms of a unique type. In our classroom, sometimes we have a periodic chart, and if not, in SP1 we do. Having said that, atoms are composed of subatomic particles, including protons, electrons, and neutrons. These particles have positive, so our protons have positive, electrons have negative, and neutrons are neutral or have no charge. So typically what we say is that in the nucleus of a cell, you have the protons and neutrons, and then orbiting the nucleus is where you would find the electrons. So protons and neutrons are in the nucleus of the atom. Electrons spin around the nucleus in paths called orbitals. A set of electrons occupy concentric shells around the nucleus like planetary orbs around the sun. Atoms are electrically neutral, having the same number of negative electrons and positive protons, except when they exist as ions. And we're going to discuss this in a little bit. Why is it important? Because many of the molecules that are in the body are ionized. And we'll find out that being able to form ions where there's an unequal charge is actually a really good way to have the body conduct reactions very quickly. More about that later. Okay, so atomic bonding. I'm going to read this and then explain it to you. So it says atoms of the same type or different types can join to each other to form a molecule or bond. Examples of molecules are hydrogen, like hydrogen gas is H2, water H2O, carbon dioxide CO2. Atoms will bond if by doing so they fill their outermost shells with electrons, a stable condition. Atoms in a covalently bonded molecule evenly share electrons in order to fill their outermost shell. So I am not going to get into orbital shells. I'm not going to get into how many electrons are in the s or p orbital. What I'm going to say is that it's the outermost shell. You don't need to know the name, but it's the outermost orbit of an atom that then can share electrons evenly. When they do that and they share even Steven, it's a very strong covalent bonded molecule that is made. And again, about half of the molecules in the body are ionic and the other half are covalent. So you have a lot of stability. It's very difficult to break these bonds. And so it lends stability to the body. Now, this is an example. It's a visual example. I am not going to, on an exam, have you identify these. But sometimes visuals help people. So H2, hydrogen gas, you can see that they are equally sharing the outermost electrons. And because they are, and this is oxygen, O2, because they are sharing their outermost electrons, then it's a neutral molecule and it has that very strong covalent bond. This is methane, CH4. And again, all I want you to see is that outermost sharing of electrons. How they share, why they share, that is the purview of a chem course. Okay, ionic bonding. Since many of the bonds in a body are ionic and it makes things go fast, let's talk about it. So atoms that can fill their outermost shell, when an electron is transferred from one to another, it forms an ionic bond. When an atom gives up an electron, it has a net positive charge and is referred to as a positive ion. When an atom accepts an electron, it becomes negative. And the next has to go into good old table salt, sodium chloride. And that's what I'm going to use as my example. So a molecule of sodium chloride, NaCl, table salt, forms stable covalent bonds in the solid crystal state. So you pick up a salt shaker. What is in the shaker is a crystal. It is a solid. You have even distributions and sharing of electrons. So the salt in a salt shaker is neutral and has very strong covalent bonds. But, once it is dissolved in water, it ionizes into a positive sodium and a negative chlorine. Thus, the sodium atom has given up an electron and the chlorine atom has accepted an electron. Because these atoms now have opposite charges, they are weakly attracted to each other, forming an ionic bond. Remember, opposites attract. So, what is happening is that sometimes, very often, we'll take in food or we'll take in minerals, and they are very much covalently bonded, but then our bodies, through digestion, was going to start to break them down and then release them to the bloodstream in its ionized form. We can get calories out of this. We can have it be essential for development of bones and things of that nature. But the thing is that when you ionize anything in the body, it is going to do that weak attraction, but it is not going to be a very stable attraction. So you can change partners. You can change ions very easily as long as they're opposites. So with the NaCl and the salt, it's just that strong covalent bond between the sodium and the chloride. Now, the reason why when sodium gives up an electron, and again, a chem course will explain the mechanism why, that's not really our concern. That it does it is our concern. So the sodium is going to give up an electron. The reason why it's a net positive is the fact that the protons are hidden in the nucleus and they don't go about sharing anything with anybody. So it's just the removal of the electron means that you have more protons. And that's what gives it the overall positive charge. And with the chlorine, it accepts the electrons. And by accepting the electron, it has an additional negative charge. Hence, it's negatively charged. Again, the opposites attract. The positive, sodium, negative chloride, they're going to be attracted to each other. There'll be a weak bond, but not a strong one, and that's what we're aiming for. Again, never going to ask you this on the exam, but it's showing you, here's sodium and chloride. Sodium gives an electron to chloride, making it positive, making chloride negative, and they hang out together, but they're not bonded to each other. All right, so now I'm going to get into another discussion about the very stable covalent bonds. Most of them are. But the problem is that 70% of our body, 70% of our cells, 70% of our blood is H2O, it's water. And the water acts as a solvent. It's into which things can dissolve, things can move. And if you are ionizing, which your body does a lot, then you have to have a covalent bond that's a little bit ionic and a little bit covalent because it wants to be able, see, half your body is covalent, half of it's ionic. So the water, which makes up most of the fluid of your body, wants to be able to interact with both. So this is where if you have a nonpolar covalent bond, that's like sodium chloride. That's like even Steven, we're going to just share those electrons and we're going to be neutral. Polar covalent bonds is what water is. So it has stability, it shares, but we're going to show you a picture in a second in which the sharing is not exactly equal. And this non-equal means that water is covalent, but it has a slight positive charge and a slight negative charge. It's the best of both worlds. being a polar covalent bond, water can interact with covalent and ionic at the same time. So when electrons are equally shared, like sodium chloride, the salt in the salt shaker, the atoms in a covalently bonded molecule, they don't carry a charge, they're nonpolar. Polarity means that there's some sort of charge, positive or negative. In some cases, like in water, electrons are not shared equally. The electrons spend more time orbiting around one of the atoms. This is referred to as a polar covalent bond. So it says water is an example. You have the hydrogen end of the H2 having a slight positive charge, and the oxygen, the H2O, has a slight negative charge. Again, a chem course would explain that to you. Right now, I just want you to know that. So I have a picture of water as a polar covalent bond. Here we go. This is the one. I'll come back to that slide in a second. Water, 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 water. And as you can tell, to see between the H and the O, it's slightly skewed so that there's a slight positive to the hydrogen and a slight negative to the oxygen. So that's the positive here, the negative. Now, because opposites attract, then water itself can bind to each other ionically, but we call the interaction of water molecules, H2O molecules, as hydrogen bonds. And so you have a hydrogen, the positive and the negative of the oxygen. They're very weak bonds. They're along the lines of ionic bonds, but they have a little bit more strength than the sodium chloride that you pour into the water. And this, so it's like in between. It's not as weak as an ionic, not as strong as a nonpolar covalent, but that's going to give water incredible properties to be able to be cohesive with each other, but also able to interact with other ionic and covalent molecules in the body. So let me go back to the polarity of the hydrogen bonds and a couple of examples of why it's important. Because of that polarity, that polar covalent bond of water, the positive end is attracted to the negative end of an adjacent water molecule. The bonds between these water molecules are referred to as hydrogen bonds, and they play a very important role in DNA. Now, we'll talk about DNA, deoxyribonucleic acid, at another time, but right now, what we're really concerned about is the fact that you have this unique property of water, and one of the unique things is the polar covalent hydrogen bonds that it can work with. So I'm going to pick that thread up in a sec. So let me just lay down that thread and let's go to water, the solvent of life. No, we could have we have tons of other solvents. We have benzene, we have dioxane, we have ethyl alcohol. We have lots and lots of solvents, but they're not as versatile as water. So that's the reason why we're 70% water rather than 70% acetone. Okay, so in fact, all of Earth uses water in the same way. It's a solvent into which bodies can manipulate molecules, then nature can manipulate molecules, and so forth and so on. So everywhere is 70% water. And of course, the answer is why. I'm just going to pick out a few things in here, and it's only what I'm going to pick out that I want you to know. So one of the things is the resist changes in temperature, and hydrogen bonding helps that. Here's the incredible nature of water. Water is in a liquid form now we use centigrade in scientific terminology, so I'm going to go with centigrade. 0 degrees centigrade to 100 degrees centigrade, water is in its liquid form. That's fantastic. That means our body, which maintains a 32 degrees centigrade, certainly is less than 100. That means everything is water and that is a very stable range of temperature. Then if you go below 0 degrees centigrade, it changes into a solid ice form, and if it goes above 100 degrees centigrade, it becomes gaseous. But for life on Earth, that's fantastic. That also means, for example, if when you form ice, um, this one right here, less dense as ice than as liquid water. And again, hydrogen bonding is because of that. Ice floats. So when you have winter and it starts to freeze, you have the ice form on the surface, not below. So I live in a pond, and every winter I have ice fishers out there. They know that they're there with their augers, and they make their holes, and they put their fishing poles in, and they do ice fishing, and they catch fish. And the reason why they catch fish is that the water below the ice is liquid. And hydrogen bonding, fantastic. The other thing I want to talk about, and this will be it, is it's very cohesive and very adhesive. And again, it's hydrogen bonding. Um, one way to think about this is that you have a tree. A tree has all of its roots in the soil, and that's when it rains. But then the tree's roots have to move that water up to the leaves, and then they can do photosynthesis. Well, you're actually moving water against gravity. And the way that you can do that is because of the adhesiveness of the hydrogen bonds. The other thing, going back to the pond, is I have insects that can skid across the pond and never fall into the pond because they're light enough, but they use what is called the surface tension between the water liquid and the air, and that gives them the ability to quite literally walk on water. That could not happen without hydrogen bonds. Okay, so that's enough about hydrogens and hydrogen bonding. I just wanted to briefly touch on acids and bases and the whole idea of pH. Again, I'm going to leave it to the chem people to get into more detail. But it's important in the body to have a neutral pH. There are some places in the body where it's quite acidic, like the stomach. It makes hydrochloric acid every day. But for the rest of the body, it wants it to be more neutral than either alkaline or acid. And this is something that I'm touching on. Will use it much more second semester when we talk about different animals. But the human body wants 7. And we know that if you have it be less than 7, it's acid, and more than 7, it's alkaline or basic. And I'm not getting too much into all of this. But it said in a container of water, a small number of water separate, it just all called dissociate, into a hydrogen plus and a hydroxy ion OH minus. When certain compounds are placed in the water, they can either be acidic with a lot of positive hydrogen ions, or they can be in a pH alkaline where they have less. So this particular slide I'm not going to cover on the exam, just as talking about a sample acid, hydrochloric acid, a sample base or alkaline, sodium hydroxide. So that's not going to be on the exam. This is really not going to be on the exam either. I'll come back to that second semester, but I do want you to know at least the pH scale and what does it mean. We like to quantitate a lot of things. So scientists found out that you could quantitate how acid or basic a solution is by measuring its pH. And I'm sure you've used pH paper and things of that nature. So body wants neutral, pH 7. If it goes below 7, 5, 4, 3, 2, 1, that's going to be very acidic, like lemon juice and Coca-Cola and coffee. We want 7. And then if you get into the base or alkaline, then that's going to be like seawater, soap, household ammonia, and household bleach. So as you can tell, you've got pH of 7, 8, 9, 10, 11, 12, 13, 14. What do you need to know? 7 is what the body wants, it's neutral. Below 7 is acid, above 7 is alkaline. That's it. And that should bring us to the end for now. So go over the PowerPoints. Obviously, stop this lecture anytime you want to take notes. And about 5 questions will be on the quiz, which you'll take after you listen to this lecture and the next. So I will see you soon.